Hello and welcome to another Maine GIS User Group virtual Lunch and Learn. I'm Patrick Cunningham and I'll be moderating today along with Laura Tessel. We're excited to have our guest speaker today speaking on monitoring regional scale high latitude landscape shifts using NASA Landsat and MODIS data. That would be Firooza Pavri, who is director of the Muskie School of Public Service, professor of geography at the University of Southern Maine. And she'll be also joined by Diana Farrell and Isaac Onis. Just a word about the Maine GIS User Group. We are an all-volunteer organization focused on the promotion of GIS education and networking and information in the state of Maine. We've been around for a few decades now, and in normal times we host a number of events throughout the year where we can all get together and share our work and learn about new technology and new techniques in mapping and cartography. Unfortunately, with the pandemic, we've pivoted to virtual events, but we're doing our best to keep the dialogue going and the education going. And that's what our Brown Bag Lunch and Learn series is all about. And we certainly encourage and hope that you would all get involved. You can do so by, obviously participating in events, attending events, but also presenting your work. Sharing your GIS work. We would love to hear from you. We're always looking for guest speakers, whether it's a conference event or a virtual Lunch and Learn. And if you're not a member, renew your membership, or maybe try to get a colleague or a friend to become a member to help us support GIS, or your company or organization. Maybe they would like to sponsor us and obviously get the free marketing and promotion opportunities that we provide, but also be really helping support the promotion and education of GIS in the state of Maine. Other ways that you can help is you can run for the board. We have elections coming up next month. I'm not sure how many seats we have open. Usually it's a few. Or you could just serve on a committee if you don't want to do the full commitment to run for the board. We are always looking for help, and we have a variety of different committees. Education, membership, programming, helping to do things like this, publicity, finance. There's a lot of ways that you can help out, and we really encourage you to reach out to us. We're always looking for the help, and you can see how to do that at our website, megug.org, or via email, megugboard@gmail.com. Here's the current list of board members, and as you can see, we do have a good variety of different professions in GIS and in different locations across the state of Maine. So that's something that we try to do and try to encourage. And just a word on upcoming events right now. What's next in the calendar is our annual meeting and elections, which will be November 16th at noon. We really hope that everybody can participate in that. We can get a good turnout, not just for voting, but also for discussing where Maine GIS User Group is at, both financially and with our goals and for the coming year, and things that we would like to do, and maybe ideas on how we might someday get back together safely in person. Or we're talking about, could we do an outdoor event in the spring? I know there are other organizations that had done some sort of GPS or geolocation events. So maybe there's some ideas that you have that you would like to share at the annual meeting. We would love for you to join us for that. I know one other word too, we do record these Lunch and Learns, and we put them up on our YouTube channel. So definitely, if you want to share the video of today's talk, you can, or if you see an interesting topic that you missed in the past, you can view the recordings there. And with that, without further ado, I'll hand it over to Laura to introduce our speakers today.
Yes, hi. As Patrick mentioned, we have three speakers presenting. First, Firooza Pavri, again, the director of the Muskie School of Public Service and professor of geography at the University of Southern Maine. Additionally, we have Isaac Onos, and Isaac is working on his master's in policy planning and management. He is also at the Muskie School of Public Service at the University of Maine. And finally, Diana Farrell, and currently a research associate at the same organization. And she also has a BA in geography anthropology and a certificate in applied GIS, also from the University of Southern Maine. Firooza, Isaac, and Diana will be presenting research on two projects, actually. The first is using Landsat satellite data to monitor changes over the last 25 years to an ice cap in the central highlands of Iceland. And I don't dare try to pronounce that ice cap's name in Icelandic. I'll let Firooza manage that. I won't take an attempt. But the second project is studying the Kuyata UNESCO World Heritage Site and its surroundings in South Greenland. This project focuses on understanding shifting land cover and vegetation patterns. This project uses MODIS satellite data from the last 2 decades. So very interesting projects, and thank you all three of you speakers, for taking time out of your busy schedules. We're very excited to hear more. So now I will turn this over to Firooza, and thank you.
And Firooza, while you're taking control of the screen, just a word, folks, if you have any questions for our speakers throughout the event, feel free to post it in the chat, and Laura and I will try to interrupt politely and just ask the questions as we're going along. This is a lunch and learn, so it's a pretty casual event. If you'd rather, you can wait till the end and ask questions at that point too.
Well, thank you, Patrick and Laura. We're really happy to be here today, and I will just share my screen. And I'm assuming everyone can see that?
Yes.
Okay, great. All right, well, thanks again for having us at this MEGUG Lunch and Learn. It's always a pleasure to talk about research and the work that we're doing at the Muskie School at USM. I'm really happy both of my students have been able to join us. So Diana Farrell and Isaac Onos, who you will meet a little later on in the talk during the Q&A session. They've both been integral to these projects, and without their work, I don't think we'd be as far as we are. So really kudos to them for taking part in this. So as Laura mentioned, we're going to talk about two projects, one in Iceland, in central Iceland, and another in South Greenland. But to set the stage, I think most of us here today are familiar with climate change and how it's impacting particularly the Arctic region. And I think this map really exemplifies the impact here. So if you look at what you're seeing here, is looking at the temperature anomaly and particularly its impact on the Arctic. If you look at that map, you see that it is that northern latitudes that are particularly impacted by rapidly increasing temperatures. And so my interest in the Arctic developed about 4 or 5 years ago. I've always been interested in using satellite data to monitor landscapes. And in most cases, I focused on wetlands and forested landscapes in the temperate and tropical regions. And so about 5 years ago, I got interested in the Arctic, and especially given all of the rapid changes that we were seeing, I was interested in looking at how the landscape is shifting in the Arctic. So in central Iceland, way up there, as you can see the arrow pointing to, and then in South Greenland as well. So I mentioned briefly that I use satellite data, and I think most of us on this call, we're all familiar and comfortable with satellite imaging. and using satellite data to really monitor what's going on the Earth's surface, in the atmosphere, etc. And so whenever I talk about satellites and remote sensing, I talk about them in the context of being space-based observatories. You know, these are these observatories out in space that are constantly looking down on Earth and sending us incredibly valuable information as to what's going on Earth and how it's changing. So we now have close to about 50 years of data that's being beamed down, you know, all the way from the early sensor systems that we had up there, Landsat 1 and 2, etc., all the way to the current systems that we have today. And of course, some of you might know that Landsat 9 just launched this past week. So we're very excited to see the data that comes out of Landsat 9. Satellite data provide an image of the Earth from a very, very unique perspective. You're looking sort of down at Earth. And so it's a perspective that we humans are not necessarily very comfortable with or are used to. We're much more used to looking at a perspective view rather than looking straight down. It also, what it provides is data that for pretty much every portion of the Earth's surface that we didn't have access to, that wasn't readily available. And so it's an incredible, incredible depository of both spatial and temporal data that will give us an incredible view of the Earth's surface. And of course, what we also have, especially in the Arctic and Antarctic regions, is we've got satellite data that extends the spectral range. So it's beyond the visible part of the spectrum and going into the near infrared and far infrared, etc., in the microwave regions. And it enables us to map ice and snow cover to higher degrees of precision. And also remembering that the Arctic and Antarctic regions are harsh environments. They're difficult to get to. Field work is very, very important, even to our work, but it's not easy to cover these vast areas. And so satellite data provide a kind of, you know, an ancillary source that really encourages us to look at the Arctic in a totally different way. And of course, as I mentioned, this incredible historical archive. So let's launch into both the projects. The first I'm going to talk about is Iceland, and the ice cap that we were focused on was the central highland ice cap called Hofsjökull. Bit of a tongue twister, but hopefully I have it close, if not correct. And the reason we chose the central ice cap rather than some of the larger ones like Vatnajökull or some of the more famous ones down towards the coast is because this was one that had not been studied quite as extensively as the others. It's also in a region that's relatively remote. It's hard to get to. And it had been seeing quite a few changes in the last few decades. And so we got very interested in really documenting the changes that we were seeing there. So we started that project by using Landsat data, which is really moderate resolution data. It has a long historical archive, so it allowed us to go back in time as well. And of course, we used the different Landsat bands, both in the visible and in the infrared part of the spectrum, to aid in our analysis. And Landsat is data that's easily used. It's updated very often. It's very, very appropriate for regional scale studies. You know, the spatial resolution is about 3-meter spatial resolution, which really does very well in the kinds of analyses that we were interested in. And it helps us document what's going on, where the changes are occurring, and how quickly they're occurring. So before we look at the data itself, it's always great to look at some images from the Earth's surface. And these images were taken by Diana, our research student on this project. And you can see in the top image, you can see the Hofsjökull ice cap in the distance. It's really quite extensive. And what you see here coming into the foreground is one of its outlet glaciers. Down at the bottom, you see the Kuyata region, which is really towards the south and west of this ice cap. It's a volcanically active region still. You still have features that, every so often you will see steam coming out of some of these areas, etc. So it is still relatively active volcanically. Really a very, very stark and interesting landscape. And you get another sense of the vastness of the ice cap from this kind of perspective. And what you also notice is on the ice cap, fields of debris, rock, earth, etc., that may have been deposited over, decades and more. And one of the other things that's really neat in this bottom image are the moraines that you see bringing down a lot of the rock and other debris from the ice cap. On the right here, you see some of the wetlands that we find on the edges of the ice cap. That's very common. We have a tremendously important wetland site to the south and east of the ice cap called the Ramsar, the wetlands themselves are called the Thorsaver, and they are a Ramsar designated site. The Ramsar is a global convention on wetlands that recognizes wetlands of international importance. So these Arctic wetlands are tremendously important ecosystems that we are interested in monitoring and seeing how they shift and change over time as well. So as I mentioned earlier, we used Landsat Thematic Mapper and Operational Land Images. These are images that we could then compare. They were, we used data that was both in the visible and in the near infrared parts of the spectrum. And in this case, you can see the sort of false color composites that are pretty typical. Just one thing to note and remember is that the red that you see on the images really are indicative of vegetation. And so you can see the sort of comparison between the two areas. And also some of the sort of comparisons over time of how the Kuyata region here on the southwest has changed, where the ice and snow cover has definitely receded over the period of study, as well as the ice cap itself. If you look at it on the left versus the right image, you can see that it has shrunk in spatial extent. And you also see that the edges of the ice cap itself have sort of experienced some changes, including considerable amount of melting, etc. Some really interesting features, especially for those interested in geology and physical geography, is this outlet glacier here. It's the Hofsjökull outlet glacier, and it's very famous. It's been studied quite extensively because it has an interesting field of moraines and drumlins that are in active sort of phase. And so it's one of the few areas in the world where we see that. We analyzed these images both visibly, so visually, and also using some basic remote sensing techniques. We created what we call classified images, where we take the spectral data and then we group like spectral signatures together in different classes. And so in this case, we were really interested in the snow and ice coverage and in vegetation, and how those two particular classes had changed over the study period. So on the left, you see the image from 1992, and on the right, you see the image from 2017. And you can see some fairly distinctive changes. So once we developed these classified images, basically using classification routines that are relatively standard in remote sensing analysis, we can also quantify the changes that we're seeing. And so one of the things that we found was a 45% increase in Arctic vegetation cover across the study site over the time period of the study, and a 23% decrease in ice and snow cover during the same time period. So we're seeing these definite signals that we can monitor through the satellite data, and it tells us a little bit about how this landscape is changing. One of the other things that we wanted to do was also to get a sense of the ice cap itself and how its margins were changing. So there have been lots of studies done, and there are sort of global studies on monitoring ice caps and glaciers. And that work has accelerated in recent years and decades because of the tremendous change that we're seeing within these systems. So we took the two time periods, the Landsat data from the two time periods of our study, overlaid them together, a very simple analysis that everyone who works in GIS is very comfortable with. And we identified some sites right encircling the ice cap. And what we did is a kind of distance measurement to see how far the ice cap had retreated or expanded over the time period. We also included one other data layer, the GLIMS data layer, which is a data layer that is put out worldwide on ice caps worldwide. That was completed in 1999. And so just to see, what kinds of shifts we were seeing. So the two data layers that we were working with is the light gray on top, which is the most recent in 2017. The darker, sort of dark gray layer underneath, which is the earlier layer from 1992. And then the GLIMS layer from 1999, which is just the sort of dark black outline that you see. And what's interesting, I think, is to note is that it's not a linear retreat over this time period, but there are time periods where the ice cap retreats, and at other times it surges. And that, of course, is due to the variability in climate, the variability in precipitation and temperature regimes, etc. So it's not entirely surprising. But we did do some calculations, and what we found is largest retreat that we found was about 1 kilometer. And it was primarily in this region right here. So there's quite a bit of retreat going on at this ice cap. We are hopeful that we can undertake some more studies and particularly look at some of the wetland regions that we find to the south and the east of this ice cap. So, just to kind of recap, of course, these frequent assessments that we can undertake using satellite data really provide us with a close, detailed understanding of what's going on in similar areas. Our methodology that we used has been used very, very frequently in the remote sensing literature. It's one that essentially reduces errors, and it provides us with a fairly decent understanding of kind of spatial temporal trends going on in this particular region. And as I said, hopefully we will be able to take this study one step further and look at the Thorsaver wetlands towards the southeast of this area, because they are going to see some fairly dramatic changes as there is more melting and as there is more warming in this region. So hopefully someday we can return there and do some more work in the Thorsaver wetlands areas. So this work was recently published last year with Diana and myself in the journal Physical Geography. So let me shift very quickly to a region that is a few hundreds of miles to the west of where we just were. And the next study I'm going to share with you is from this very sort of tip of Greenland. It's known as the Kuyata region in South Greenland. And Kuyata is a UNESCO World Heritage Site. So there's been enhanced sort of focus on this area. Some of you may know that this area, the Kuyata region, as well as farther up along the western coast of Greenland, was where we found Viking settlements in the medieval period. So Vikings coming primarily from Iceland settled down in these two sort of settlements in Greenland and flourished for quite a few generations. However, there were some changes that happened in the climate. It got much cooler, and those Viking settlements vanished. But there are still archaeological remnants from that area, and there is enhanced sort of focus on the area because it's an area that we want to help preserve for future generations. It's also a area where currently in South Greenland, there's the sort of similar agricultural practices that we perhaps would have seen back when the Vikings had settled here during the medieval period. So what we decided to do in this project is look at seasonality and variation in vegetation and how that was changing and whether it was changing because of changing climatic conditions. So if you look at, this is a slightly more closer view of the Kuyata region. You see a lot of the old archaeological sites that we've been able to identify and excavate and are now in the process of preserving. However, intermixed and sort of dispersed with these archaeological sites are modern day agricultural establishments as well, farms, and particularly sheep farming that's very, very popular in this region. One doesn't necessarily think of sheep farming with Greenland. It's oftentimes associated with, of course, the largest ice cap in the Northern Hemisphere. Nonetheless, sheep farming is very common in this region. So once again, always start with a few images from the ground. Here's one of those archaeological sites that has been excavated and is being preserved. This perhaps some of you recognize as the Valsay Church, very, very famous from that old, from those old Viking settlements. You see some other farms and structures, stone structures that they have been able to preserve. These are, like I said, interspersed with modern day farming enterprises. And you can see these farm homes and farmsteads, etc., that are really intertwined with this old historical legacy of farming from several hundreds of years ago. So this is the Igaliku site, I believe, from this region of South Greenland.
Firooza,
yes.
we do have a question. Someone asked how you were able to remove the cloud cover to get a more accurate measurement of the ice and snow cover in your study area.
Yeah, that's an excellent question. And in fact, if I can call on Diana, because Diana engaged in a lot of that analysis, she would be able to tell us more. Shall we come? Try to come back
to that question? Sure.
Okay.
Just chime in when you got it going. I'll see if I can help you out.
All right. So talking about, of course, the Greenland study, what we did in this study was use a different data set. NASA MODIS, which is a moderate resolution imaging spectrometer. It's also moderate resolution, but the spatial resolution of MODIS is quite different from Landsat, as we'll find out. But what we wanted to do was, as I had mentioned, understand those seasonal and decadal shifts in vegetation cover across the region. And we were going to, we were in the process of mapping this variability and generally monitoring this coastal fjord landscape. And interesting, sort of what we've seen in other parts of the Arctic is as temperatures increase, we are seeing more greening, definitely, in many, many regions of the Arctic. But what scientists have also found is more cases of what we call quote unquote browning, which is where the vegetation perhaps while it might be, the temperature might be warmer, perhaps there's insufficient water. So precipitation may be insufficient, which causes, in turn, the vegetation to die. So we were on the lookout for that. We wanted to see whether there would be similar trends of greening or quote unquote browning patterns that we also saw in Kuyata. And one of the things that we're engaged in currently is really understanding the human impacts from these landscape changes. So we know that there are farming communities in Kuyata, and when we were in the field about 2 years ago now, in the summer of 2019, we were talking to some of these farmers in these farming communities who talked about sort of seeing those shifts in climate affect their own operations. So reduced precipitation was giving rise to all sorts of concerns with their sheep flock, etc., which we'll talk about in a bit. Looking at this region, from this top image is from a plane coming in to land in the region. You can see the ice cap, it just extends all the way to the horizon. It's pretty amazing to watch. But of course, when you're on the ground, you are right there in front of these numerous, just dozens and dozens and hundreds of coastal outlet glaciers that are bringing in fresh water into this North Atlantic region. And they're just tremendous to be up front and close to. The outlet glaciers can be hundreds of feet tall and calving constantly, etc. But what was very, very interesting to me was to just observe the landscape around this region. You know, the notion or the conventional wisdom, of course, is that it's very Arctic, bleak, very, very little by way of vegetation, etc. And that may be true in certain areas. For instance, this region, which is relatively close to the ice cap. Ice cap is less than a half kilometer away from here. Even here, you see that there are mosses and lichens and short shrubby vegetation that has taken hold in areas where there are conducive conditions. You can see that on all of the really tall, craggy peaks, the sheer cliff regions, you know, any foothold, and you would see vegetation, which is rather interesting. So these are really hardy plants that survive under these conditions. But then you go to some of the other areas, especially in the fjords and the lower fjords, where it is somewhat warmer, you will see this kind of subarctic vegetation, willows, you know, stunted trees. They're shorter in some cases and stunted in growth, but nonetheless, you see a fairly rich and vibrant vegetation. And that, you know, to some of us was really quite surprising. And of course, in the valley regions of the fjords, you see the sheep farming enterprises. And here are some of the images of these sheep farms. They're quite extensive, you know, and they will allow their sheep to roam free and graze through the grazing season. And then as winter approaches, they collect the sheep and bring them into the barns, etc. So a really rich, fertile area. And that has been, you know, given rise to a fairly productive sheep industry. So, as I said, we use MODIS. MODIS is at 250 meter spatial resolution as opposed to Landsat, which was 30 meter. You know, in this case, MODIS made much more sense because we were looking at a far larger region, and we were also very, very focused in on vegetation. We really weren't looking at sort of, you know, other landscape categories. It was mostly vegetation, and MODIS is great for that. MODIS provides a ready-made vegetation index, an NDVI, normalized difference vegetation index, which essentially is using the near-infrared and the red spectral bands in order to enhance the vegetation signal. So we are capturing greenness, vegetation greenness, its vigor, etc. And what MODIS provides us is just with this sort of very systematic, regular interval of data. So we collected MODIS data from May through September, the growing season. between 2000, the year 2000 and 2020, so a 20-year time frame. Resulted in 60 plus image sets that we had to comb through, and both Isaac and Diana did an amazing job combing through all of this, preparing the data and getting it ready for the analysis. And so we were looking at vegetation trends in our initial analysis, seasonal shifts, and how what changes might we be seeing over this decade period. So at the backdrop of this, of course, is the changing climate. And if you just look at long-term temperature trends, this is a 50-year time frame, and we are in the 20 years, so 2000 to 2020 in the bottom graph. You notice something that's rather subtle but pretty marked is the earlier period. You have relatively, you don't see the kind of higher trend that you see in this later last 20-year period. So there's been definitely a shift that we've moved from the cooler temperatures that generally fell below the long-term anomaly, the long-term mean, to those that are now primarily falling above the long-term mean. So clearly we're seeing shifts. So let me just share some of these images. This is the region that we've been focused on, particularly focus on this kind of inverted hockey stick, for the lack of a better way to focus your attention. This is the general Kuyata World Heritage Site. We looked at early season, May, peak season, July, and then late season, September images. And remember, we looked at over 2 decades for every year in the last 2 decades. I'm not going to show you all of the images, but I'll show you a few snapshots. So this is from the year 2000. Here is 2010, and you can see some pretty big differences, both in the early season images and then in the sort of later time period as well. And what's really interesting is that 2000 was a bit of an anomaly, especially in the early season. It was warmer, it was wetter, and that perhaps contributed to a more vibrant vegetation signal during May in 2010. And then we look at something very recent, just 2020, so last year, from the growing season last year, and you can see something similar, right? The early season, peak season, where you see a lot of really active growth, and then late season where things are senescing once again. So we can look at average NDVI, or the normalized difference vegetation index, and we can look at it for the May, July, and September series from the early part of our study to 2020. And what we find is, well, there's a lot of variability, especially in the early season data, especially for the May mean. In certain years it's high, certain years lower, not entirely unexpected. The second line that you see here is the September data. And what's pretty stark in the September data is this sort of steady increase. And so what that's telling you is, as you get towards the more recent years, you are seeing a vegetation signal into September, perhaps not what you had seen in earlier years. And the July data, perhaps a slight decline, overall, as the overall sort of linear trend. We're still analyzing this data, so we're going to tease out some, details, etc. Is this really a kind of downward trend in the July data set, or, is it just some of the variability that we're picking up? We're still looking into that. So then we kind of get the big picture, and then what we do is we go through each of the seasons more carefully. So you can map out the seasons side by side, as we've done here, and you can really see the sort of differences pop out. You can do that for July. And you really see, the sort of higher the NDVI value, what that's indicative of is more vigorous vegetation and a stronger greenness signal. So clearly we are seeing some of those differences play out. You see the late season signal, and yeah, it's sort of a mixed signal for the September, but remember these are only 3 time slices. We're looking at each year individually as well. So what we do is a simple difference, and this is something that Isaac, our student, can talk about in greater detail as well. You know, minusing one image from another. Generally, the reds indicate greater greenness in 2020 versus 2000. Okay, and you can see that for the May, for July, and then for September, and then the blues, which you only see in kind of mostly in the July image and the September image, is that greater greenness in 2000 versus 2020. So we're looking at all of these in more detail. And what we can do is, using the NDVI, we can calculate, we can measure the sort of spatial extent of vegetation as well. And so we've done that for the 20-year period. And we're going to look into this a little more closely as well. And once again, you see that September signal, where the spatial extent vegetation seems to be going slightly on an upward trend, whether it's sort of, you know, pretty flat in the case of May and July. So just to quickly wrap up, we really need to do a lot more in terms of the image analysis for the Greenland study, and then eventually publish the results. And both students are working on that, and we're all kind of putting all of the analysis together in the form of a journal publication. We're going to expand on this vegetation analysis and focus on the farming and agricultural trends that we're seeing next. We're hoping to go to Greenland again in 2022 if things are better with the pandemic. And what that will allow us to do is field verification, surveys, and all sorts of things that will really complement and enhance the satellite data analysis that we've done so far. And then just quickly, I think, you know, I'm sure we here in this group don't need much convincing how incredibly revolutionizing space-based imaging has been for the way we really understand Earth systems. You know, I've worked in this field for the last 20 years, and just in the last 20 years, we've seen just incredible changes and developments. So we will keep using satellite data and satellite imagery, look at the Earth and see how it changes and monitor that change. And just as a last slide, I don't know if I can do this, but this is one of the outlet pictures in 2019. You just get a sense of the incredible power of the water that is coming out of the ice cap. 2019 at that time was one of the warmest summers on record. I think 2020 then beat it. But we saw numerous of these outlets of incredible fresh water that was entering into the fjords in South Greenland. So I will stop there because I know we are out of time, and stop sharing, and hopefully we can get our students on the screen as well.
Sure, yeah. We can do that. I was just curious, did you say, Firooza, what drew you to study Iceland and Greenland?
You know, it's interesting. I think it was spurred on by a trip that I took. I believe it was 2016 that I had the opportunity to visit Iceland, and I completely fell in love with the Arctic landscapes. So that was the start of it.
Mm-hmm. Oh, great. And I know that I have some friends actually that just went to Iceland on a vacation. So I know that some of those restrictions are, or at least lifted a little bit, so you can get back at least to Iceland. I'm not sure, of course, what Greenland is doing, but so hopefully you can get back there soon. I do see that Isaac and Diana have joined us, so that's great. Diana, I've got to unmute your phone. I just got to find that. Let's see here.
Okay, can you hear me through the video now?
Yes, we can. Yeah. Do you
Oh,
want to? That's great. Do you want to take a stab at that question we had on cloud coverage?
sure. So when we downloaded the Landsat 8 data, we used level 2 surface reflectance data, and that, which has the top of the atmosphere correction, so that was very important. But within that, they have quality assurance bands. And the quality assurance bands has several layers, one of which was cloud shadow, several versions of clouds, more than I knew existed. But so we created a mask. I imported that from SNAP, which is the remote sensing tool, the Sentinel application platform from the European Space Agency. That's what we did our remote sensing analysis in. So I imported that layer into ArcGIS, created a mask, and then applied that back on the data back in SNAP. But when I did that, then running the classification that Firooza showed you, where we broke it down to land, vegetation, water, it kept really confusing with water, and we were having a lot of trouble with that. So, and this is with the k-means unsupervised classification, so there's no training data. So we ended up just kind of doing away with that. I mean, we have the boundary for the physical, the visual shape, but the classification itself seemed to be pretty good at picking out the cloud pixels. So we ended up just going with that.
Okay, great. We do have a question for our panelists. Were there potential differences in the sensors, data processing, interpretation methods, et cetera, between the 1999 GLIMS data set and the 92 2017 data sets that could explain some of the apparent expansion of the I'm not going to get that, the main ice cap you studied between 92 and 99? Or was that expansion completely due to environmental factors?
That's a great question. So the GLIMS data and how they calculated it was somewhat different. They also use Landsat, so it's the same data set, but with GLIMS, it was actually a hand calculation. So they digitized the edge of the ice cap, and they were doing that for all of the glaciers and ice caps across the globe. So yes, there would be some of those sort of differences in methodology, I think, that would account for perhaps some of those differences. But, you know, I think for the most part, I would say it, you know, when we were looking at our analysis, I would say it was mostly environmental conditions that accounted for most of the changes that we were seeing. Diana, do you want to add anything to that from that Iceland analysis?
Sure. So we did talk about this a great deal before we published the paper, that it did come from completely different methods. However, in looking over that, we found a really good correlation. So we felt like, although it's probably not down to the centimeter or even who knows, but we felt like it was certainly representative enough just to give an idea. And that's why we included that data set in the paper, not so much as a detailed analysis, but just to give the overall perspective of how things fluctuate over time. And that it, like Firooza said, it's not just a linear, that and it's recorded in multiple other historical events that backed up that GLIMS data set, historical accounts in Iceland from historical documents. So we felt pretty comfortable in including that.
Excellent. In the Greenland study, Firooza, you spoke about some of your NDVI comparison and your technique that you use there. I don't know if Isaac would want to expand on that, or?
Yeah, Isaac conducted most of the change analysis. So Isaac, would you like to talk about that?
Yeah, sure. So real quick, the great thing about MODIS data is that each year you have the same dates, more or less. So we picked, you know, September 30th for each year, except for leap year, which was off by a day. Late July, early May. So just with that context, it has allowed us to kind of play around with ways to compare each year. at that level with the raster data, the NDVI data. Otherwise, if it was different dates, it'd be hard to justify trying to compare one from the other. But really, we're still not sure our confidence in what we've done so far. Basically, what we've done is we're just using a simple raster calculator technique where we subtract, you know, the September 2020 NDVI from the September of a year prior, and just seeing what is a difference. And mapping that has been a little bit of a challenge, just in the symbology and how to effectively portray that. So we've looked into some reclassifying techniques as well, but we're still in the process of it. And the goal is to really be able to quantify the changes, which is on our to-do list.
I have a comment to add to that, if that's okay.
course.
One of the things that I did at the beginning of summer was we did go back, as Isaac mentioned, we went back and reclassified all of the data. I went back and kind of did an analysis to see. So NDVI runs from -1.0 to 1.0, if you're familiar with that equation. So we looked at where does the vegetation really kick in, and we found, I did kind of a random point analysis and found that, and we did a literature review, and anything really below like NDVI of 0.15, really there was no vegetation. So we went and removed all those values so that our latest data set is really only reflecting NDVI values of 0.15 to 1. So that was an enhancement, that was a refinement. So now we're really just seeing vegetation coverage. And so that was a step in that direction that Isaac just mentioned of kind of improving the quality of the data set. First, we wanted just a big picture, what's everything doing? And now we really wanted to zero in on just what is the vegetation doing. And so refining those values really helped with that.
So I have a question for you. Have you found that the governments of Greenland and Iceland are, you know, receptive to helping you with your research, with promoting what you're doing in studying climate change, and that it's so in their face and so real to them, more so maybe than in other parts of the world?
Yeah, I absolutely think so. I mean, I think they're just so much more keenly aware of the changes. And the changes are so obvious that it's almost like you cannot ignore them. So in Iceland, you know, we got data from their meteorological association or organization, and they've been collecting a lot of long-term data on all of the ice caps and the glaciers across Iceland and whatnot. And they were very interested to see the results from this study, and were extremely supportive and provided us with climate data, etc., that we needed. In the case of Greenland, you know, most of our analysis so far since we started the project has been remote. It's been using the satellite data and doing the remote sensing work. And we're hopeful that going back next summer, we'll have an opportunity to really interact with folks there. We did some of that in 2019 before we started the satellite analysis. And all of the sort of farming communities that we spoke of said they were very, very interested to see the data. They were very interested to learn more about how long-term, how this region has been changing and what that might tell us about the future. So I'm really excited to hopefully go back there next summer and share this work with them, because that's, you know, that is always the sort of coming full circle for our work, which is you do the work, but then also share it with the communities that can benefit hopefully from it. And, you know, there's one thing I will add is when we were in Greenland in 2019, and we talked with some of the farming communities of what they would like to see, you know, what are their needs? You know, one of the things that came up was to look at how the region has changed over time. And of course, satellite imagery is just the best tool to use to really understand that over the long term.
Excellent. Do you think Obviously, looking historically, this isn't appropriate, but going forward, doing change detection, that you would benefit from, maybe LiDAR data or drone collected data at all?
Yeah, well, why don't I have, one of our assistants, research assistants talk about that perhaps? I've talked enough, I feel.
I
Does
mean, I know
anyone want
li-
to
I
take
know
either
LiDAR data
drone or
can-
LiDAR as a
LiDAR
possibility?
certainly can, have NDVI type data, so.
Yeah, I mean, I'll just add, one of the limitations with MODIS data is that it doesn't have that great of resolution. I can't remember exactly what it is, but it's like 250 meters,
50
I believe.
meters, yeah.
Yep.
Which, we've been playing around with some next steps, and it's really hard to really pinpoint certain areas to cross check over time. So any other way to increase resolution and quality is a way to move forward. Oftentimes you're just limited with money or access or things like that. I think drone mapping would be really interesting, but it goes to, you need to have a drone with a NIR sensor, which I don't know. I don't even know how much that would cost. But I mean that, as the future, as we move forward, these things could be more feasible, for an institution like us or something, for sure. That would definitely be a goal.
So one of the things that we saw in Iceland that really helped us is areas that were potentially problematic. There may have been some confusion in the land classification and some gray areas, if you will. I was able to go there, thankfully, in 2019 and kind of do some ground truthing. And we had a plan before I went of exactly where to go, limited by access. Like we said, remote sensing is for remote areas, but I was able to get there, and boy, it was a rocky ride. But so we were able to get some ground truth data. So these areas, yeah, like Isaac said, it's hard to get there. So yeah, I mean, any other sensor we can get on this, awesome. But sometimes remote sensing is all we have right now, and it's very powerful.
And I mean, it seems like that would be an opportunity to educate the governments there about the value of investing in that type of data collection, certainly in the LiDAR area. Yeah, I was thinking the resolution issue might be
Yep.
something. I'm not seeing any other questions at this point. Is there any last closing comments any of you would like to share? Oh, wait, I do have a hand raised here. George has raised his hand. I don't know if I can unmute you, George, but let me give it a shot. You want to? Oh, I'd have to promote you to panelist, George. Maybe you could put your question into the chat for me. Probably typing away furiously right now.
Well, I'll just say it's been tremendously exciting to work on both projects, especially with Diana and Isaac, because they're such fantastic students. And it makes the project so much more fun when you have a team that's working on different components, and both Diana and Isaac have their strengths. And so it's sort of a team effort where we put all of our brains together to work on this.
I second that.
I second that.
Do you feel like actual applied research is really a difference maker as far as learning the next level of GIS as opposed to just in the classroom?
100%.
100%, yeah.
Yeah, I mean, you do learn a lot in a classroom for sure. I learned remote sensing by taking a class with Firooza. But at least in my opinion, so much of learning in applied GIS or any other related software is from problem solving. And we've had to do some serious problem solving. And so just the amount of time solving things that weren't even, or not solving things, hitting dead ends, I've just learned, immeasurably.
I would agree with that. I mean, the remote sensing classes with Firooza are tremendous. We both got interested in it because of that, but then you get into the real world project and you're like, oh, this isn't going like the one in the class. And so you have to figure it all out. And we even changed the entire data set that we were originally going to use based on roadblocks that we hit, data just not even being available. So yeah, and we're very happy with how it's turned out, but it certainly took a couple big right turns that we didn't see coming, and that's research.
It sure is. Well, and if either of you wanted to come back and give a presentation on some of the challenges you had to do data set, I know you think that's dry, but we have a lot of folks that would love to hear about that and maybe even help you troubleshoot things. These talks don't all have to be about successes, because science, sometimes you don't find, it's failure too, right? It's mistakes and figuring out the best way to get to the solution. If you ever feel like that, feel free to shoot us over an email. We would love to have you back. I think that's probably all the time we have today. So again, thank you all for speaking and sharing your research with us. And thank you, Laura, for helping out. And with that, I'm going to close up shop for today. So hopefully we'll see you all back next month, and enjoy the rest of your day. Thank you, everybody.
Thanks, everyone.
Thank you.